We start our session that will talk about retrieval. So Mark Hamazaspyan from Metric will present what's happening in the world of visual document retrieval. Please do.
Hey. So hi everybody, thank you for coming and let's start. So we'll talk about the visual document retrieval, what is it, talk about the recent research and what we in Metric are researching right now connected to the visual document retrieval and overall retrieval connected with not only textual modality. Okay, so first of all, let's talk about the retrieval augmented generation. As you know, we use retrieval augmented generation to give extra knowledge for our LLM in order to answer questions from in-house data which cannot be publicly available. So retrieval augmented generation can be connected with open source LLMs, with closed source LLM, with anything else. And retrieval augmented generation is consisted of these two parts. So it is the retrieval phase. So given a user query, system retrieves the relevant information from our knowledge base or database or any other place. And there is also the generation phase. So we take this information, give it to the LLM, and it with a query, it generates answers to the query based on the its knowledge and also extra information that we given to it. So overall, we will in this talk we'll concentrate on the retrieval phase and not the generation phase. Okay. So what is the retrieval stages that usually are happening underneath? So we have the external knowledge, we need to process it, and it includes the text chunking, storing it in a vector DB or in other place. Then we have the user query. So user gives us query, we do query augmentation, we do some different experiments and processing on the query, and eventually for the given query, we retrieve some relevant knowledge from our database or from our information base. So there are many search methods that are happening. It is traditional BM25, vector search, or the hybrid of the two. And let's see what's the difference between the taking text as a knowledge and external knowledge, and instead of text having documents. So in that case, there's a couple of additional steps happening. So we have the document, and in order to understand and keep the information of the document, we do a text extraction with it. So we run OCR, we then get this text. So maybe we need to do some layout processing. Maybe we need to make it more beautiful in order to LLM to understand. We do text chunking. So we stored all of this in the DB, and the rest is same. So while doing this with documents, there are many questions arising overall. So how do we, with the text it's easy, but with text also there is something happening, but text is usually raw information. But here we have in a page we see a layout of the page. So how do we keep the layout of the structure? So do we use Latin prompting? Do we put it in HTML tags or markdown format? And how do we decide whether this amount of size of the chunk is a good one? Maybe we keep small chunks and we miss information. Maybe we pick a big chunk, and because of that, LLM is getting extra noise and is not able to correctly answer query. And also, a lot of documents, they are charts, graphs, and images which cannot be captured by pure OCR models. So there are a lot of questions how to do it. Then the solution comes here by the guys who invented ColPali. So instead of doing all these difficult processing, OCR and stuff, we just embed the image. So we create a model that takes the image as an input directly instead of compared to the text. Okay, so this is the overall method. So here we have the standard retrieval, which is the upper part. From the page, we take OCR layout, and then we embed those information. And from the right part, we take a text query, embed, and there's a maximum similarity, like any similarity score between them in order to understand which document is for the specific query. So that is the standard. The ColPali guys are saying that instead of doing the OCR, just let's break down the page into 4 parts in this scenario and give these patches directly input to the VLM model. So here we introduce the concept of the VLM into the retrievals. And as they are vision language models, they can input the image directly. Okay, so the model architecture is quite simple. So we have, originally there was the SIGLIP as the image encoder, and there is another LLM, Gamma as a LLM decoder. So we input image goes to the SIGLIP. There's a linear projection to have the same dimension space as the text. Then we concatenate the image and text tokens with each other, embeddings with each other. And then all of that concatenated tokens go to the Gamma 2, and we get the text output. So the original paper says ColPali, but it actually can be called anything. So we can have like polygamma, we can have Quen VLM doing this, we can have small VLM. So it's not boundary to the polygamma only. And even we can have like any encoder and decoder structure together. So it can be SIGLIP with Quen LLM, it can be Quen Vision and like arbitrary embedding model, which is a text embedding model. Okay, so this is how do we get an embedding model from the LLM? It's very easy. The standard LLM is giving predicting next tokens. So we just remove this linear and softmax layer, and we get embedding of the inputted text instead of doing the predictions. So it's quite simple. And here another thing that ColPali guys has introduced into the vision retrieval part. So here, there are many architectures happening. So we have like 2 different models, and the first part giving embedding for a query and document separately, and then we do similarity calculation. We have the document and query. They are like from the beginning being interacted with each other in middle 2 cases. There are also examples what kind of models there. And there is this Colbert late interaction introduction in the last part. So here we have query and document, and the main difference between the last and the first is that in the first case, we only have 1 embedding for query and 1 embedding for a document. In the late interaction case, we have as many tokens we have. Each token is becoming embedding for the query and document. And then max similarity scoring is happening during the similarity calculation. I will talk about it a little bit later. But basically, the main difference is that the first and the last one are offline retrieval methods, meaning that if you have like a lot of documents, you can separately calculate all the embeddings on documents, store them, and later when a query comes, you just do the query processing and similarity calculations. In the like middle two, they are online. So every time for each query, you need to process documents as well. So because like from the beginning, there are some things happening between them. So more on the late interaction part. So here you can see, let me explain the process that's happening. So for each query, in this case, our query is being encoded into 3 tokens, and our document, let's say, to 4 tokens. So for each query token, we are calculating the cosine similarity with the maximum document token and taking that token for specific query 1. And then we do it for all queries, and in the end, we just sum these similarities and we get the whole similarity for the query and document. So whenever we have like 2-3 documents for this query, the document which maximum score will be highest, it will be the representative document for that query. Okay, and ColPali has integrated this part into their model. So these are the document embeddings, these are the query token embeddings, and the maximum operation is happening there. Okay, and just another thing. Usually when we like talk about embeddings, they have the embedding, they are outputting an embedding dimension. And for by-encoder, not the late interaction models, we have usually embedding which has quite big hidden size. For this case, the hidden size is 2048. And if we, like for normal retrieval models, is okay because we just store one embedding with this size. But for the late interaction, the embedding, the number of embedding outputs can be around, let's say, 800 to 1000 for an image or a long text. So in this case, we will be saving like 1000 on 2028 embedding metrics in our storage, which is computationally much costly than single embedding. So to overcome this issue, we just compress the embedding dimension to a smaller thing. So instead of having 1000 with 2048, we just project with the custom text projector our last hidden states to 128 embedding dimension. So in the end, we'll have 1000 on 128. It is still higher than storing just one embedding with 2048, but because the performance of this late interaction model in this case are much higher than just one embedding, this is at least some workaround in order to save space. Okay, so in the above part is the late interaction process formula, and let's talk about the loss that they are using. So they use in-batch pairwise cross-entropy loss. It is some kind of a modification of usually used info NSE loss. In info NSE, we say that for each query, we calculate the similarity of positive document in a batch and similarity of negative pairs in that specific batch, and we say that the positive similarity should go up and the similarity of negative documents should go down. The only modification here is that instead of calculating similarity with all negative pairs, we just take inside the loss the similarity score of the hardest negative pair. So we have the positive pair minus hardest negative pair, and we want to increase the subtraction there. So the positive similarity goes up and the similarity of negative sample goes down. Okay, I wanted to also show what are the data samples that were used for these kind of research and models. So you can see there's are like pages of different documents. It can be from any field, chemistry or finance or anything else. So usually we have the query and we have the document page. So for this query, we need to retrieve and find from 1,000 pages the correct page where the answer to this query most probably will be in. And you can see like there are a lot of graphical and visual information that will not be captured if we just treat this document as text. Okay. One more thing that is also introduced is the Vidore benchmark. So we have these models. There should be some place that we can also understand whether our model is performing good in tasks. So this is the specific benchmark specifications. There are a couple of academic tasks and practical tasks from different domains, a number of queries, documents, all this present here.
Can you describe the task? I'm sorry, it's you give a document and you ask a question and it should find the right part of the document, or?
Yeah, you have like many documents with 1,000 pages. So let's say you want to do a question answering. And you cannot like give all this document information to the LLM for the answer because it would be like answer is usually in one page. So here the retrieval part is that for this query we retrieve and understand what are the most relevant pages for specific query. You get those pages and then you proceed later with answering question or anything else.
The data sets have the labels which are the right pages, or they only have the right answers?
No, for the like in the benchmark, each query says that each query has its specific document page as a positive. And maybe there are other benchmarks that like don't say just one page, like specific representing 5 pages that the answer can be there. Okay. And here are the results of the ColPali guys. So different things, but the important score is 81 in the end. This is the original results from the paper, and I will also present our model results later.
Again, what are these numbers? It's retrieval.
It is NDCG at 5, meaning that for each query we need to rank 5 documents, and also we need to rank correctly their importance. Yeah. Okay. This is all about the ColPali. Now let's talk about the research that we are doing on top of this. Okay, overall we have these specific goals for the research. We want to create this state-of-the-art model for visual document retrieval, and we want to do it open source, meaning that we'll give the weights and publish everything for others to use. So contribution to the open source, and we also want to have a multi-model embedding model working with not only text and image only, but with other domains such as video and audio. And let's say why it really matters. First of all, current reality is that most of the retrieval is done with text-based things. And if we have like video and audio, we usually have captions and transcriptions of the video and audio. And then we search with just text-based models. Here we can have like one embedding model that is giving text, image, video, audio embeddings in a shared semantic space. And we don't need to have additional processing for videos and audios before doing any search. And one of the in the end impacts is it would be very cool to have a video search or audio search model which will say, let's say we go to YouTube, we just search in a video, find scenes where the person is entering a red car at night, and it specifically brings these like small clip of the video, and similar thing with the audio. So the impact would be very broad and very big. And we have earlier this year we had open source these 4 models. Our research results were these. So we have like models starting from 2 billion to 7 billion. These are fully open source. You can find it in Hugging Face. So far we have around 50,000 downloads on them. And this is the things that we already done and open source. Just to give a basic idea, we usually this embedding, our embedding model is trained taking the base model of Qwen 2.5 VL. So it's a 3 billion parameter model. We do the ColPali-style training as the ColPali guys introduced. We gathered around 250k query image pairs, and the training was for 5 epochs. And we didn't train the LLM, we just put the LoRa layers on the LLM and train with the LoRa strategy. Just important thing here, we didn't like touch any visual, any weights of the visual component. Only the LoRa layers are only attached to the LLM of the entire VLM. And another model which is a little bit different is the Qwen Stella. In this case, as I said, the Col model can be combination of any 2 models. In this case, we took the only vision part of the Qwen, and we took already existing text embedding model, which is the Stella, and we just combined them and trained with the same strategy as the previous model. With same data, same training. And let me show the results. So as of March 2025, which was before, in the Vidore benchmark, we were scoring the highest rankings. So for over a month or 2 or 3, we were in the first positions with the 7B, 3B model. And also the smallest model, which was 2 billion, is in top 10. Okay, then Vidore 2 was published. As you can see from this slide already, like having scores around 81 is kind of a sign of benchmark being close to the saturation. And in our cases, I just noticed I don't have the numbers here, but the first model has a score of 90.91, which in case of any benchmarking is also saying that this benchmark is not perfect. And Vidore 2 was published, which is much more difficult benchmark compared to the Vidore 1. It's not perfect either. There are many inconsistencies there, but still the original score was around 60% of the score of our models, the previous ones before Vidore 2, were around 50 in this Vidore 2 benchmark. So overall, it shows that this benchmark is much more representative of having globally good model. And we continued to do some proper training, some more tricks to have a better embedding model, and we compare the results on the Vidore 2. Right now, we have in-house 2 models. We haven't published them in open source yet, that are scoring 63.8 and 62.8 for the Vidore 2 leaderboard. It is the top 1 and top 3 ranking right now. And there are other models like NVIDIA 4B, that's a Llama nanometer retrieval model close to us, and yet another models. So let me talk about the findings, because you can see there's just not only names, but also it's a checkpoint and models attached to it. Let me explain what this means. So first of all, the first finding is that whenever we train this embedding model or usually do any training, there is a good practice of averaging some checkpoints throughout the training. So averaging our model with 3 other same, this was the top 3 ones. So averaging with different checkpoints, weights after the training, we saw that overall the model score goes up. So before it was 60, and when we did the averaging, we got 62.8 score, which is, okay, there's a slight mistake here. So the top 3 model is 62.8. The top one should be 63.8. Yeah. And let me tell you what's happening there. So we said, okay, averaging checkpoints is a good idea, but usually those and it worked. But those checkpoints are kind of all they have been trained on the same data, meaning they're like the only difference is that more steps have been separated them. So what will happen if we have trained like this model with different strategy or on different data sets? And in order not to do all these trainings, we just took a couple of other models from the Vidore leaderboard, which has the same backbone as us. And most probably they were trained like with different strategy and like with different data sets than us, because not like everything is fully reported for sure. And when we did the averaging of those models with us, which is like around 4 model averaging, we saw that the score had jumped around 3%. Like beforehand, all these models were having scores around 60 to 61. And with just simple weighted averaging, we were able to get change score of 36.8. So this is very interesting and cool finding that we got from all these experiments. Okay, let's recap. So with these things, we kind of, let's say, completed 2 of our research goals, which is creating the state-of-the-art model for visual document, which, if we believe to the benchmark, the goodness and thing, we were in the like top 1 position. And we contributed to the open source because we open sourced our models. Anyone can like go download and use. And now last part is like left. So how do we get like a text, image, and video, audio embedding model? Because as we on a moment. As we did this image embedding experiment, the last one with this course, we like added like a lot of other things, and we spent a lot of compute and time of gathering specifically document data. Like we went over 10 million text image pairs. We collected it from the open source Hugging Face dataset, around 200 of them. Then we did like in-batch negative training, hard negative mining to get better data samples, which it decreased our 10 million dataset to 1.5 million. And then we did hyperparameter tuning experiment and model merging experiment. So for the past like 6 months, we were doing all this. And this is only to get image embedding visual image retrieval model. So if you want to do same for the video and audio, a clear problem is here, because for this, like doing for adding each modality, we need to go gather specifically that modality data, clean it, hard negative mining, hyperparameter tuning, and other stuff. Which is time and compute-wise overkill overall. And we thought, what if we go with this strategy? So text retrieval is kind of the most well-known and already done a lot of million times research direction. What if we take this our VLM and we pre-train it with the text-to-text retrieval data? So from VLM, we get model that is a retrieval model, and there's like a lot of well-defined retrieval datasets with hard negatives in Hugging Face. So we just can take all those datasets with minimal processing and just train this text retrieval model. And later, for the stage 2, we can just create and get a small sample of any modality we want. So instead of 10 million or 1.5 million samples, we can just gather 100,000 high-quality hard negative data and fine-tune the stage 1 model with this modality. So overall, the strategy is this, meaning that text retrieval, very easy to find data and fine-tune. For other modalities, just spend less time to get this 100,000 and even less data. So let's see how do we validate this. Okay, we gathered these 20 high-quality hard negative document data that I was talking about, with which is around 23,000 examples. Then we fine-tuned. We have 2 fine-tuning experiments. First, we take the ColQuen base, which is the Quen 2.5 VL 3 billion, the base model without touching. We train this model on this 23K example data, and then we take the same model, do the text-to-text retrieval pre-training, then after it fine-tune on the same 23K data. And let's see what is the differences here.
Sorry, ColQuen base is some sort of already tuned, LoRa tuned on top of Quen, right?
ColQuen is actually, yeah, it's misunderstanding. No, ColQuen is just the base model with the base weights of the Quen VLM. It is just
exactly the same, no changes.
No changes.
I see. So what you did before in the previous slides is not here.
The second part, so strategy 1 is doing text-to-text retrieval, which is the second point. So the ColQuen text-to-text.
So this is not the metric models as a base. This is, you again start from Quen from scratch.
Yeah, every experiment we do, we start with the Quen.
I see, okay.
Yeah. So Quen is a VLM. Our doing is converting into the retrieval models. Yeah. So the only difference of these two is training base model on document data, and compared to training base model with text data, then with the same document data. And let's see whether our hypothesis that text-to-text retrieval will help us is true or not. And here is the results on Vidore 2 with just training 150 steps with the 23K data. So I don't know whether you can see, there is the yellow line, not yellow, the bluish line and the orange line there. So here you can see both models are learning. However, the text-to-text model, which is a text retrieval model, already after even with 50 steps of training with 23K data has scored above 60%, which is the current like very close to the top part of the Vidore. And the base model is slowly learning, but I think it might take like much more time and resources to get to the level of text-to-text pre-trained data. So with this experiment, we kind of validated the thing that pre-training with the text-to-text model will help us with small but high-quality data to fine-tune it to other modalities. And let me talk about the findings that I haven't mentioned so far. So we understood that text-to-text pre-training gives enough retrieval abilities for transferring it to other modalities, meaning that the learning part is just mainly converting text retrieval to other modality retrieval, not the retrieval task itself. Hard negative mining is a key. So whenever we change the data from in-batch negatives to hard negative minings, we always see improvements. So whenever possible, even from the first stage of the training, we can do it with hard negatives and will give us better scores. And one more thing, the VLM, Qwen VLM is a causal model, of course. It's a VLM, so it is producing text in the end, and that's why it's a causal model. And we thought, okay, for the embeddings, we don't have this text generation task, so why don't we just remove the causality mask and we have to have a bidirectional BERT-like structure there. And it is also like a question whether it's good or not. And we trained the same experiment with causal mask and without causal mask, and we saw that for on Vidore we have okay, this is also not correct. Okay, don't look there, listen to me. Removing causal mask helps us to have 2% higher score. So for the embedding models, we remove the causal mask in order to have a better score. In our case, it worked. So this should be without causal mask. Vidore score is 2% higher. Basically, this is all it. We, let's say, also have checks to have text and image modalities. And the next stages of our research is to broaden it to other modalities like video and audio. And the exact steps that we are planning to take is having text model training, text-to-text retrieval model trained, and then gather some good amount of data from video and audio and do a fine-tuning for hopefully shorter amount of time for this video audio data, and get a multimodal retrieval search model. Okay, I think that's it. Thank you very much for coming. If you have any questions, you are welcome. You can find me on my LinkedIn, and this is the metric Hugging Face, where you can find all our open source models, and future models will be also published there.
Thank you. Do we have questions? Before you think for questions, I have many. So this new data set, new benchmark that you mentioned, it is about only detecting the right pages, right, in a way?
Yes.
And then this is not the final goal, right? Later you will use it to do something. And when I want to understand how this is really correlated with the final performance. Like, you probably have more downstream benchmarks or applications where you use this, right? And in those cases, in this final like downstream tasks, probably you can already compare to like large models like Gemini and others, right? I want to understand what is the relationship there. Like, if you need text extraction from a 1,000-page document to answer some question, how do these models perform compared to just throw this 1,000-page to Gemini and ask the question?
Yeah, I think, okay, so I see two problems with the Gemini approach. The first one is that whenever we are giving all these documents, we are also giving like extra noise information to the Gemini. Of course, like year by year, they are getting smarter and they will neglect this. But another thing is that there are a lot of like companies that do not want their private data being inputted to the Gemini. So they rather have, and even like a smaller model, in-house model, to work on their data and their documents and not share with anyone. So privacy.
But what is the performance? I get that. And you know why I'm asking? Because many people ask me this, like, for example, I want to create a chatbot for lawyers or accountants that know the content of rlist.am, right? The all Armenian laws. And my initial reaction is that, guys, rlist.am is available freely online. So if you ask Gemini to look into rlist.am and give you answers, that's probably the best. But then, yeah, there are cases where you can't do that. So my question is, do you have any feeling or measurements? How well do these models perform against Gemini for these downstream tasks? Like if it was available for you, is it like same level quality or it's like way behind and then we need to improve these numbers from 60 to, I don't know, 90 to make it work?
If I'm not mistaken, there is also scores with text retrieval model plus OpenAI things in a benchmark. But I don't remember the score, which means they are lower. That's why I don't remember. But in our experiments, we didn't really compare with the thing that can also answer questions, because right now we're focusing with the search and retrieval. We compared it with text retrieval models in one of our projects that we were doing, and the scores are I would not say very high, but the scores that we're comparing with the text model are similar or even higher with document embedding models.
I see. So you think that improving these retrieval models a lot will help in downstream applications now? It's not that this is already good and we should focus on LLM, because if your next step after retrieval is still a small LLM, then maybe the bottleneck is there, not in retrieval or this.
No, usually, yes, I understand. So usually, in the cases that we encountered, the questions were not really that difficult for them to answer. It is more difficult to
find
the right page than the answer, because usually, and even in industry, let's say you are saying that give me the revenue of this company for this year, and if you have it like in the page or in text, it's much easier even for smaller models to answer. But finding it through all documents that have many revenues for other years and stuff like that, it is trickier.
Can you comment on multilinguality of these models? So you rely on multilingual understanding of the vision encoder of Qwen, and then probably also Qwen's own multilingual aspect, right? You know why I'm asking this? So when you generate images with these modern models, right, like Gemini, Flash, or whatever, they can write text in the image pretty well in English, but have no idea about Armenian, for example. If you ask it to draw an image with an Armenian text in it, it's very bad. And I think that it's kind of connected to this, right? It means that vision encoders are not really good at Armenian understanding, and all this benchmark could probably be translated into... Did you have an experience there?
Yeah, so we mainly rely on the language capabilities, multilingual capabilities of the Qwen. So I don't, for it to work in Armenian images, I think we need to, as I said, we are not changing any ways for the vision part. So in this case, we might. But I can say that these embedding models are working good on the main other languages like French, German, Italian, Spanish. And the Vidore itself is multilingual. So there is also some of the data sets are translated into French. And I would say the thing is that the same data set is translated to the French part. So the score for the English data sets was like 61, but for the same French data set, it was around 59.5. So it's lower, but it's...
Okay, yeah.
Yeah.
True, I see. And my last question, if you think about improving these models, do you think that visual encoder part should be improved?
We have that hypothesis as well, and we even tried to add LoRa layers on train or only train attention and stuff, and it didn't work. It's usually same or worse, and we like Quen is already enough good model that it has a lot of good visual understanding from documents and stuff. So we understood that with this training we are more of like interfering with its previous knowledge than helping it.
Oh, I see. And is it even possible to understand the quality of, like, the bottleneck of visual encoder? Like, I don't know, maybe some other evaluation tasks that are not related to the interaction between image and text, but are image only. So that, but yeah, it's hard.